In this video, we're going to be looking at an example that asks us to represent an integral of a function as a power series. So we're asked to evaluate the indefinite integral of inverse tangent of x over x dx as a power series, and ask then what our radius of convergence is. So in order to do this, we'll start with our power series representation for inverse tangent of x, which is sum from n equals 0 to infinity of negative 1 to the n, x to the 2n plus 1 over 2n plus 1. If we divide by x, we get sum from n equals 0 to infinity and negative 1 to the n, x to the 2n, because it'll just kill off that plus 1 piece in the exponent, and then divide by 2n plus 1. Notice that the right-hand side is defined even when when x is equal to 0, because remember our convention is that 0 to the 0 power will be 1 here. And if you go through the work, you can check that the left-hand side has a limit as x goes to 0 of 0 as well. So if you redefine this function as equal to inverse tangent of x over x for all x not equal to 0 and equal to 1 for x equal to 0, I think I may have said the limit was 0 to start with, but the limit is 1 for certain. Okay. Then this function is continuous everywhere and has that power series representation. Now we're ready to integrate, and then this is just using power rule to integrate. So we'll add 1 to the exponent, divide by the new exponent, so that's why we had a 2n plus 1 squared here, because that'll come from dividing by the 2n plus 1 when we integrated. We're asked to do an indefinite integral, so the plus e is going to stay there. There's nothing to solve for. So that gives us our power series representation for that indefinite integral. Radius of convergence of the original power series started at 1. So, again, that was what I said, assuming that we define f of 0 equal to 1. That's important, because if we don't have that definition, then that function's not defined. So the radius of convergence is also 1.